All right, continuing on here in Unit 1, this is Chapter 4, kind of going over right now things like qualitative versus quantitative data. Eventually working our way into some tables here, but basically we're going over different types of data. So if you want to recap on the last video, that could be helpful for you. But we're looking at now ratio kinds of data. This has everything. All right, this is everything. Zeros, decimals, any kind of number you can think of, and difference is meaningful as well. But the key with that zero is it's a natural zero. It means nothing. So as we just established, money in a bank account, that's an example. Right? There's $0 in your bank account. It literally means nothing. Okay? Let's recap. Right? Well, many variables such as age, income, and years of education are quantitative. All right? Quantities or numbers or numerical. Others aren't. Right? For example, gender and race, your brand preferences, modes of transportation, types of occupations, those, all right, aren't. Those are qualitative. Those are different types of categorical data. Quantitative are something like grouped and placed in categories, right? They are sometimes able to do that. And when we do that, those are put into marginal frequency and distribution tables, right? So qualitative data often encompasses, right, qualitative data encompasses two categorical variables, right? Oftentimes, these data may or may not have dependent relationships. One might depend on the other. These data can be displayed in what we call two-way tables. For example, the cuteness factor, all right? Let's take a look at this example. A Japanese study had volunteers look at pictures of cute baby animals, adult animals, or tasty-looking foods, after which they tested their focus in solving puzzles. Okay? Yes, who wouldn't set up this test? And here is what we got, right? Level of focus, all right? Low, medium, high. Then over here we have baby animals, adult animals, and tasty food. The level of their focus. All right, pictures viewed in the row variable where the column is how much they appeared to be focused. Okay, and by pictures viewed, I think they mean like they were showing them pictures of it. One method of analysis, this data involves calculating the totals for each row and column, which that's simple, right? I think we can all do that. Just add them up this way, add them up this way, we find our totals, right? And there you go. Not too bad. And notice how the totals either way seem to add up either way to the same total out here of 250. These totals are placed in the right and bottom margins of the table and thus are called marginal, right? Because they're in the margins, marginal totals. Should make sense, right? These are outside our margins, right? So those are your marginal totals. These marginal frequencies, because of frequencies right here, right, can then be put in the form of proportions or percentages as well. Just like these can be put into percentages, right? So taking a look at that table still, right, the marginal distribution of the level of focus is, right, level of focus, 90 out of 250, 95 out of 250, 65 out of 250, and we have our percents there. Again, I will repeat. If I'm going too fast, you pause the video. That's why I write everything down on the screen so you can pause to see it. Okay, so there are your frequencies. You can display the distribution in bar graphs then, right? This is the low, medium, and high, right, and their percentages. Great. And similarly, we can determine the marginal distribution for the pictures as well. I could do this the other way, right? The pictures viewed, I could go down this way. 65 divided by 250, 85 divided by 250, 100 divided by 250, and get my percents there. And I can represent that in a bar graph. Okay? Same idea. Right? So, there they are. So we can kind of see roughly, there's the 26, there's roughly 34, there's 40% for all of those. It's the pictures viewed. Conditional frequencies, though, and distributions. The marginal distributions on the outside described and calculated earlier do not describe or measure the relationships between the two categories. For this, we must consider the information in the body of the table, not just the sums in the margins. Right? For example, we are interested in predicting the level of focus from the pictures viewed. So, we look at conditional frequencies for each row separately. In the last example, what proportion or percentage of the participants who viewed baby animals then had each of the levels of focus? So they first viewed baby animals and had the levels of focus. Baby animals, levels of focus. Alright? So, baby animals, the total is 65. Not that. Baby animals, levels of focus. That's why it's 5 over 650, 65. 20 over 65, 40 over 65. The conditional distribution can be displayed either with groupings of bars or by a segmented bar graph chart, where each segment has a length corresponding to its frequency. So here is kind of like a bar graph of the levels of focus of just baby animals, or one big bar up to 100, and then it's divvied out. Okay? Either way works. But the spacing of that bar is just kind of leveled out with what means what along the way. Similarly, the conditional distribution for the participants who viewed adult animals. So adult animals and their levels, right, would be 30 divided by 85, 40 divided by 85, 15 divided by 85, all right there with their percents. And for the participants that viewed the tasty foods, right, tasty foods, we would just do, again, 55 divided by 100, 35 divided by 100, 10 divided by 100. Same thing. The following bar charts give these visual aids. This would be the baby animal ones, all right, and their percent for each one. The adult animal and the tasty foods, all right, all for each one. And I could have put them all together on the same one, and the one with the lower, right, you can see which one's bigger now. So I kind of like these. This one looks bigger for medium, and this one looks better for high, right there. I see it all together. Here's another example. A study was made to compare year in high school with preference for vanilla or chocolate ice cream with the following results. I know, great data, right? Year in high school, preference of ice cream, vanilla and chocolate. Okay? So what are the conditional frequencies of each class? Well, in order to get that, I'm still going to need totals down the side, right? So basically, freshmen, I got my 30. I would get 36. That'd be 27 and 33. The point is, after that, conditional probability for freshmen, what they like. Freshmen that prefer vanilla is 20 out of 30. And freshmen that prefer chocolate would be 10 out of 30, right? Sophomores that prefer vanilla, 24 out of 36. Sophomores that prefer chocolate, 12 out of 36. Juniors that prefer vanilla is 18 out of the total of 27, right? And juniors that prefer chocolate, 9 out of 27. And seniors that prefer vanilla, 22 out of 33, and seniors that prefer chocolate, 11 out of 33. In such a case, where all the conditional frequency distributions are identical, we say that the two variables show perfect independence, all right? In each case where all the conditional frequency distributions are identical, we say that the two variables show perfect independence. They're all different. However, it should be noted that even if two variables are completely independent, the chance is very slim that the resulting two-way table will show perfect independence. Sorry about that. Will show perfect independence. Take a look at another example, right? Suppose you need heart surgery and are trying to decide between two surgeons, Dr. Fixit and Dr. Patch, and you find out that each operates 250 times last year with the following results. So, here's Dr. Fixit and Dr. Patch. And when they were operating, if you go down the list here, we see how many died and how many survived, and how many died and how many survived, right? Okay, so instantly, people tend to look at this and say, yo, more survived. Gotta go with Dr. Patch, right? Well, what I'm going to explain here is, whom should we go to, right? Well, Dr. Fixit, 250 patients, right here, had 190 survival rate. So 76%. Whereas Dr. Patch had a survival rate of, right, 200 out of 250 or 80%. We're probably going to want to go with Dr. Patch from the looks of this data, right? So, you would think your choice seems very clear. However, everything may not be as clear-cut as you think. Suppose that on further investigation, you determine that the surgeons operated on patients who are in either good or poor condition, because that's huge. This right here is good condition, all right? So this person right here had only 68 total people who were in good position. He had 137, right? And that's poor condition. And people in poor condition, he had 130 survive. So note that adding corresponding boxes from these two tables gives the original table. So my point is, if this was the table at the very, very end, the total that we said, here is in good condition and bad condition, that died. In good condition and bad condition, that died. All right? So the point is, yeah, it looks like he had more people total that died, but most of them were also in poor condition. He barely had any that were in good condition and died. So how do the surgeons compare when operating on patients in good health? Well, if they were in good health, right, Dr. Fixit operated on 68 people in good health, and 60 survived. That's 88%. And Dr. Patch over here, 120 survived out of that, which is 87. Technically, he did better on patients that were good, in good health. Dr. Fixit's patients in poor condition, Dr. Fixit in poor condition, 71.4%. And then Dr. Patch, he actually did better in both categories. Dr. Fixit did better in each individual category, right? Dr. Fixit does better with patients in good condition, and he does better with patients in poor condition, right? But together, all right, Dr. Patch looked better. But Dr. Fixit does have a lower overall patient survival rate. So overall, right? So how is it possible? The problem is an example of what we like to call Simpson's paradox, okay? Simpson's paradox is when a comparison can be reversed when more than one group is combined to form a single group. The effect of another variable is masked when the groups are combined. Together, it looked like, right here, together, it looked like Dr. Patch should be better, right? But separately, Dr. Fixit should be better. All right, the effects of one another on them. So in this example, we realize that Dr. Fixit operates on many more patients in poor condition. And because of that, that's why his overall rate went down. Therefore, these patients in poor condition are precisely the ones with lower survival rates, and they should be. And thus, even though Dr. Fixit does better with all patients, his overall rating is lower, and our original table hid the effects of the variables related to the conditions of the patients. All right, so that kind of summarized some stuff with the two-way tables. We're going to have tons of examples of these to look at, but for the time being, that ends our notes on Chapter 4.